All right. Good afternoon, evening, everyone. I'm Felix from the University College London, and I will talk today about virtual reality and accessibility. Some of you might have seen David's presentation yesterday about the evolution of VR game controls. I will now pick up on why it is so difficult to make them accessible and how the problem is not actually with the controllers themselves. But first, let us take a step back and look at traditional video game controls. One way to measure the complexity of game controls is a concept called control dimensionality, proposed by Swain et al. And used by Mostercream and Nystrom. Assessment is done in two steps. In the first, you determine the basic movement scheme by choosing one of the following: one-dimensional movement, like left and right, or just up and down; two-dimensional movement, left, right, up, down; and three-dimensional movements, left, right, up, down, or in, out. On the second step, you add a CD for each secondary dimension of control. A full one for each additional movement dimension, such as strafing, acceleration or braking, or rewinding, fast forward if you have a time axis. And half a point for each embedded action, such as jump, attack, rotate, and that's usually just a button. And if we go now through, take this metric and now go through time, at the beginning it's very easy. The original Magnavox Odyssey had just two knobs, so our CD is just two. And with the Nintendo Entertainment System, with its bi-directional D-pad and 4 buttons, we arrive at a CD of 4. And if we now go through the time, the first PlayStation controller, Nintendo 64, the first Xbox, all the way to the current generation, or near current, we see that input has become increasingly more complex. And there are some devices that escape this classification completely, such as the Kinect. What's the indirectional control type if a user's body is the input device? Virtual reality is very similar in that regard, but we will pick that up again in a moment. The bottom line is that as time progresses, games and game controls are getting more and more complicated, and a disabled player is in danger of being outpaced by those requirements, and that actually happens. Dr. Matthew Dalgleish, a researcher up from Wolverhampton and born with an impairment himself, describes in one of his papers how we are suddenly excluded from video games when we came out, simply because it assumes that the player can use both hands to hold and operate controls at the same time. Despite the increasing complexity of game controls, accessibility in traditional games is a very active topic. Before we go into the method of making video games accessible, though, I would like to take a moment to talk about the difference between making accessible games and making games accessible. There have been many attempts at making games tailored to certain impairments. One-button games are an example of this. Better games that can be played solely by using one single button as input. And they work pretty well, because one button is something that pretty much anyone can use. In a similar vein, there are games that are built specifically for wheelchair users, with and without VR. They work very well because they are tailored to the specific populations. They also suffer from some issues. They are usually mini-games, one-offs, or proof of concept. They lack the budget of big productions and are unlikely to produce much of a return either. But there's another aspect that I feel is often overlooked, and that is the social component. Video games are a hobby that they can enjoy and share together with their able peers. We are potentially all equal in video games. People with impairments are interested in them in the same way the rest of us is. This was shown in a study by Beeston et al., where they did a survey of 154 disabled players in cooperation with the organization Able Gamers. They showed that the taste in video games of disabled players is not different than that of their able peers. They want to play the same games, and they want to play with them. So while bespoke games certainly have their role, it is the games that are already out there that we need to make accessible. And that's true for traditional games and VR games. Studies by Mott et al. And Gerling et al. That disabled players were enthusiastic about playing VR. And again, one of the motivations they give is that they want to participate in something that their able peers enjoy. So let's take a look how traditional video games become more accessible. You have probably seen most of these measures before, and some of them might even consider them standard by now. One example are different color schemes to help users with color blindness, or subtitles to help users that are deaf or hard of hearing. But there are also more exotic ones, such as co-piloting or bespoke control interfaces. Copiloting is actually quite an interesting feature because it allows to merge the input from two controllers into one even before the input is passed on to the game. So the game does not, and it does not need to, know that there's assistance used, but it allows an impaired player to get help by a second person or themselves through an alternative means of input. And alternative means of input have been around for a while too. Organizations like Able Gamers in the US and Special Effect here in the UK have been helping disabled players with customized input solution. Copetti et al. Published a solution that includes elements of today's co-piloting as early as 2008 and spun it off into a commercial product for both the PlayStation 2 and 3. However, their product, the JP Emulator, is now discontinued, and while I don't know the exact reason it went under, it's likely that it suffered from the same issues a lot of other bespoke controllers suffer. Bespoke production is expensive and often prohibitive, including potential buyers and further shrinking the small niche it is in the first place. And until recently, these control interfaces were mostly developed without any official support by the manufacturers of the game systems, which meant that any update or new generation means starting at square one. However, this got better a few years ago when Microsoft published the Xbox Adaptive Controller. It does not look like much of a game controller because it does not come with many buttons, but that is somewhat the point. At its back, it has a row of 3.5mm plugs, so you can connect it to your own hardware. It does impose very little restriction how these input devices look like, and that is its power. It finally gives you an official and somewhat inexpensive interface that you can use as a platform for your accessible configuration. Buying the buttons and switches from Microsoft themselves is still expensive, but you can also build them yourself with very little skills required. Here you see a few switches I built just with plywood and cheap electronic components, and they work just fine. So now we have a somewhat comprehensive picture of how accessibility is approached in traditional video games. Let's look at VR, shall we? If all that stuff works well in traditional games, it is certainly applicable to VR as well, right? Oh, there's still a placeholder in here. One moment. There we go. For some things, that is indeed true. Subtitles in VR exist, but are not very widely spread. Same goes with visual accessibility. Some games such as Beat Saber, which you see here on the right, are allowing you to change the UI colors for better accessibility. There's also this very interesting project Seeing VR, published by Zhao et al. In 2019, where they demonstrated a whole toolkit for visual accessibility, with the majority of the tools not even requiring support by the game. They just sit on top. However, if we starting to look at making VR interactions more accessible, our previous approaches start falling apart for a variety of reasons. First one is simply about dimensionality of input. Kinect, virtual reality resists our attempt to classify it with a CD scheme because the dimensions of movement input are not as easily determined. The head movement, the head and the hands, or whatever local motion controls the game might have. What if it's teleport? How do you put that in an axis classification? But even if you look at it in a naive way, simply counting the individual means of input as individual dimensions, the difference between classic and VR controls become apparent. Standard Xbox controller has 2 sticks, 2 triggers, and 14 buttons, giving us 18 potential dimensions of input. The Valve Index system has 3 tracked objects, each with 3 axes for location and another 3 for rotation. Then each of the handheld controller has 1 stick, 1 touchpad, 1 trigger, 1 sensitive grip surface axis, and 4 buttons. Altogether, we end up with 48 dimensions of input. That means input with a much wider variety. However, a bigger issue though is how actions are characterized inside of the games. And actually that's the problem right there, because the actions are not actually characterized inside of the game. In traditional video games, there's a very clear separation between the player character and the player. We have the game character inside the box on the right side, and the player outside on the left side. Communication goes through the input interface. Important to note here is that the player doesn't actually perform the action they want the character to do. The player presses a button and the character raises the weapon. Another button press makes the character reload the weapon. Both actions are rather complex and require a great deal of dexterity, but the player is not performing them, or the interaction is abstracted through the game's input scheme. This makes things like remapping inputs and co-piloting very easy because all you need to touch is the abstract interface on the side of the player, on the left half. This interface is relatively low in dimensionality and interchangeably between games means that it's not a complex problem to solve, and you can even reuse it for a great deal of other games. The button that reloads the weapon in one game is swinging a sword in another. Your input device does not need to care, because you're working on the left side of the interface. All that changes is what actually the character performs in the game. In VR, however, the player is in the box. They are the game character. And as such, the interaction is not abstracted anymore. Instead of giving the character a command that leads to a dexterous action, player now needs to themselves need to perform it with their own hands. Instead of a simple button press that we can remap, we suddenly have a complex series of hand movements that we need to deal with if we want to make this action accessible for someone who cannot perform these motions themselves. But hey, we are clever, right? We just write an application that takes control over the user's hands and replace the motion. But that does not quite work yet, because how do we know where the weapon is? In a traditional game, it's always in the same place, but in VR, the player can hold it how and wherever they want to please. Maybe that's not a problem too. We can probably deduct that from the position of the hand we're holding it. Next question, are the right or left-handed? In VR, that matters. Well, we can add another toggle for that, but just replaying a recorded motion still won't work because while a rifle can be anywhere, the magazine pouch is on a fixed position on the player. So we now need to dynamically calculate the path between the pouch and the weapon. Okay, now we got it working. It's fairly complex, but it works. It now works for this one specific weapon and the one player. Now we just need to do that for the other rifles in the games. And the shotguns, and the pistols, and whatever this thing here is. And that's just for one game. If a player now wants to play Beat Saber, we have to do all that effort again. Back at square one. Sure, this is all somewhat of a worst case. You can probably cut down and simplify motions and be clever about guessing what is required when, but the core problem stays, and that the player is not commanding actions, but executing them, which makes generic remapping nearly impossible. You might counter that I'm excluding here that VR controllers still use buttons, and that they still offer the same abstract interface that we see with regular game controls. And you're not wrong. The role of these buttons is different than with traditional game controls. In 2D games, buttons are the means of input, the way you give commands to the game character. In VR, they are not used like that. They're often used much less and in more of an accessory fashion, often just to simulate pushing buttons and objects that you hold, such as a safety on a gun or to pull up a virtual menu. You can absolutely map these buttons, but as they're not controlling the main interactions with the game, this won't do you much good. So does that now mean we can't do something such as co-piloting? Not necessarily. As a matter of fact, we spent some time trying it, but what we came up with is not quite the same as co-piloting as we've seen it from consoles. The first thing we dropped were the symmetric control interfaces. With the Xbox co-pilot, both players look at the same TV screen and use the same type of Xbox controller, or at least two controllers with the same abstract interface. In VR, that is not really feasible because it would mean two people in two VR sets. That itself is not a problem yet, but it leads down a road where you need to think about which of the two players controls the head movement. And that is a fast track to motion sickness. And that's not speculation on my part. This has been tried in the past by researchers with people having their heads physically linked together. And that did make them sick a lot. So instead of two people in VR, we wanted to have a co-pilot outside of VR, still using a screen and a regular Xbox gamepad for input, and the player inside of VR. This obvious gives us another problem, and that is that we need to do a reduction of dimensions. As I said earlier, the Xbox gamepad versus the VR system is 18:41, so we can't simulate all the input. We need to find a way to approach this in a more clever way. We eventually did this by looking at VR players most likely will need, and that is movement of the whole body and of the hands. That is still more access when we are having available, but if we are not insisting on having all that happen at the same time, we can just about deal with it. So what we came up with at the end is a control scheme where the co-pilot can take over control over either one of the hand or the full body and move them in the virtual world. Admittedly, it's a bit awkward. It will not make you reload faster in a game, but it allows players that are not having a very large range of motion with their arm to reach for virtual objects that were otherwise inaccessible to them. So this is how this looked back in spring 2020. This was our first prototype, and only body movement was available at that time. We ran a small pilot study with 8 people to explore how they would react to it. They experienced both roles and were then interviewed by us. And yep, there you go. The results were encouraging. Most reported no signs of motion sickness, they had fun, and they found both roles engaging. But we did prefer the VR role. Interestingly enough, there was way less communication than we expected, but that might have been the game, because the roles were quite clearly split when playing Space Pirate Chainer. One player was shooting the robots, the other one was moving the virtual body. We presented these findings July 2020 at XR Access, and we have also published the source code on GitHub if you want to take a look at it yourself. After the positive response, we extended the application to now also extend the user's reach. While not in the context of accessibility, there is previous work on reach extension in VR. You might be aware of the go-go technique, where the user's arm movement is amplified after traveling a certain distance. There's also HOMA, where the user points a ray and the hand travels to the object. They both have some problems though. While they all extend the reach of the user, these techniques add additional controls that increase the complexity of the application, and they can interfere with existing controls, they risk overwhelming or frustrating the user. HOMA also has the additional drawback that it requires knowledge about the objects in the scene and whether they can be interacted with. This information is not easily obtainable outside of the game and makes HOMA unsuitable to be used as an accessibility tool for general VR applications. Copiloting now would address this problem without increasing the complexity of the application or increasing the workload of the player. Compared to our prototype for the body movement, we changed 2 things. First was obviously that instead of moving the whole body of a pilot, Copilot now takes over one of the hands. Either one, but only one at a time. Once taken control, they can use the gamepad to move the hand around. Pilot is not completely losing control though, they can still move the hand. The motions will be applied in the new frame of reference. The second change we made was forced by the ongoing pandemic, but it is useful nonetheless. We made it remote. For our first prototype, the 2 players needed to be in the same room, which was a huge no-no at the time, so we implemented streaming of video and input for a UCL-based relay with a pretty good latency. One feature that both our applications had in common is that they work with any SteamVR game. Any. The way we achieve this is by interfacing with a library called Input Emulator. You can find it on GitHub as well, and it uses library hooks to manipulate matrices inside of SteamVR framework. Through it, we can do this manipulation to the pilot's input without ever touching the game. That is a huge advantage because we don't need to wait for game developers to make the game accessible, and we can provide these accessibility tools with a uniform interface across multiple games. I think that implementing accessibility tools at the level of a VR system is the best way forward for those reasons. We then ran another study, though a rather small one. Through the complexity of the setup and the lockdown, we ended up with this ridiculously small participant pool of just 4. We asked them to play Job Simulator, sitting down with and without assistance. And again, feedback was fairly positive. They found it useful. Most importantly, they found the game more enjoyable with co-piloting than without, which is exactly what we are looking for. If you want to get more details on this, there's a publication that we did at IEEE VR. The paper's available online. One major limitation of these first 2 test balloons was, though, that they were both performed with abled users that were limited by, which we artificially limited by telling them to sit down, which was mostly because in the middle of a pandemic and with our relatively complex test setup, it was not very easy to recruit people, especially not people with impairments. However, in the context of a Prime VR project, we recently ran another study together with our partners on Malta and Cyprus, St. James Hospital and Kinesiphoro. The goal was to investigate the accessibility of off-the-shelf VR technology for populations with musculoskeletal injuries or stroke. I will keep information on this fairly superficial because we are still analyzing the data and plan to do a proper publication at a later point in time. But there are a few takeaways that I want to share because I think that they can help other therapists and software and UI designers to make the VR app more accessible. First one is be mindful of the age of your population. This is particularly important if you, like us, work on using VR for therapy, because you will then need to accommodate users of all age group, and especially the elderly if you are looking at populations recovering from something such as a stroke. For an older age, you will have a set of additional requirements that not necessarily come from the condition you are actually treating. Elder people are more likely to have other health issues. They are not as fit and flexible as us anymore, neither mentally or physically. And they will need more time and more breaks. Also, you have to deal with more aids for hearing, seeing, and walking. So the key to work around that is to plan accordingly, especially around time and how often you give instructions. Expect that everything will take longer, but also keep individual exercises on the shorter side to accommodate for breaks. If you have a patient coming for multiple sessions, consider getting lens inserts with a prescription to save the hassle with glasses. If you work with patients that require walking aids, make sure your application can be played seated, and that you have something in place to rotate the patient in the virtual world. Apply subtitles if your patients are requiring hearing aids. Second thing is be mindful of the knowledge that your population brings. Somewhat ties in with our previous point. We had a respectable number of people struggling with using the computer mouse in Jump Simulator. The reason for this was simply that they have never used a mouse in their life before, like the physical one in real life. Sounds mad at first, but the average age of the group of people was 70. They have grandchildren for that kind of stuff. So for them, the exercise was much harder than anticipated because they had to learn not only how a mouse works in VR, but also how a mouse works in general. So be careful with depicting new technology, and maybe ask yourself what would happen if you would give the object in question to your nan. Would she know what it is? Would she know how to use it? That kind of question. Third thing, be mindful of the realism. VR systems offer a more realistic interaction with the virtual world than the abstract user interfaces we are used to. If we want to grab something, we can actually do that by closing our hand around the index controller and gripping it tighter. What we observed, though, was that this invited some of the patients to expect other naturalistic gestures as well, that the game actually did not support. To provide some examples, they tried to push objects around with their hands, lift objects by trapping them between their hands, or actually using the index finger and virtual hands to push the button of the virtual mouse. And none of that worked. For those of you who did software development before, you can probably imagine how the first two ended up. Physics engines in games really don't like being pushed around. We had a lot of coffee cups flying through the world. And all of this is confusing for the user. It blocks the flow of the game. There are a lot of issues around that. So what's your realism and what expectations do you evoke in the user? If you have one or two very natural interactions, but the rest is rather abstract, that will create an inconsistent user experience. And it works the other way as well, with having a large number of abstract interfaces and only a few natural ones. This is obviously a very hard problem to solve because we all have different expectations, and some people will try doing things that you have never thought of. One way to work around that is the testing. Show your application to a variety of people and see how they interact with the environment. And pick people from various backgrounds and ages. It's a very easy trap to fall into if you only test with the people in your company or just your office. Don't only recruit weird participants. The fourth point is offer assistance, but don't expect it being used. Of course, we offered all the patients we saw to make use of the co-piloting assistance, but the adoption was very, very low. Only very few people wanted to actually use it. Of course, we asked them about it, and the reason for it were very simple, and it actually had not much to do with the assistance itself. They did not want to use it largely for two reasons. Saw the struggle and difficulty as part of a therapy. This is particularly relevant for the musculoskeletal injury population, where the therapy is all about using the injured limb as much as possible. And so they did, which meant avoiding the assistance even if it made the task super hard or even impossible for them. Second one was that they did not want to rely on someone or something else to perform the task. That was particularly prevalent with the stroke population, where the main goal is to regain the ability to perform everyday activities themselves again. So again, the use of assistance was tied to the therapy goal, though in this case, it was a little bit more of a pride thing. So how can we work around that? Should we stop putting effort in assistances? I don't think so. As we have seen, people do use it. But you should limit your expectation on how helpful your assistance will be, and it would also help to consider how your assistance interacts with the goal of a therapy. As you have seen, there's a link here between patients and wanting to use the co-piloting and the goal of the therapy. And that is what you want to avoid. Your assistance should enable the patient to do the therapy, but not take anything out of the therapy. Now, I think we now have a pretty comprehensive picture why accessibility in VR is not trivial and why it's different from many of the established methods that we've developed for more traditional interfaces. However, I think it's very important to tackle those challenges, so we do not exclude a large amount of people and can use VR to its full potential together. We are now in the beneficial position that we are relatively early in VR becoming a popular medium and could leverage this early design influence to build for accessibility instead of potentially needing to retrofit in 10 to 15 years down the road when regulations are finally caught up. And that's it. Thank you. We have another 15 minutes left in the slot if anybody wants to ask any questions.
Yes. In terms of having the like co-piloting assistance, or even trying to like map some of those like complex controls, like you were saying before about having that agency outside the box